Hello. We're getting ready to start the second lecture, the second chapter we're covering in the book. I am instructor Robert Unseld, and we're going to dive into the system unit, specifically processing, hardware, memory, the whole kit and caboodle. So we're going to break this lecture into two parts. We have a lot to cover. We'll probably do about 35 minutes for the first part of the lecture and then do the remainder. So let's get started. With every lecture, we're going to have some learning objectives. We'll take them one by one. The first one is we want to understand how data and programs are represented to the computer. In essence, we want to demystify how this software, this high-level stuff, turns into commands for this actual physical hardware that we see. We want to understand the functions of the hardware components. We want to know what's inside that system unit and be able to describe the devices, the hardware, the CPU, the GPU, the memory, the buses, all that stuff. We want to be able to know that at the end of this chapter. We also want to look at how the computer CPU and memory components understand the instructions, how they process instructions, how they actually get access to data, how they can do things with the data, and how they can move on. After that, we want to be able to know some of the strategies that can be used for speeding up computer operations, and even to name them and evaluate them. And this is stuff that will help you in your personal life as you have a computer that begins to age and you want to speed it up, and the most cost-effective way to do that. And then finally, we want to list or look at some of the future technologies. What we think some processing technologies will be in the future to make computing better. So those are our objectives. A brief overview of what we're going to look at today is we're going to see how computers represent data. We're going to explain how memory and the CPU are arranged with one another. We're going to look inside of that chip, that black box of the chip that makes all the magic happens. We're going to find out how the CPU performs tasks, how it does processing. And then we're going to see how we can make faster and better computers in the future. So the overview is very simple to our, it's not simple, very similar to our learning objectives. So first and foremost, let's talk about how data is represented in a computer. Now, you and I represent things with words, with our language, and we need to understand what the digital language is. What is the digital representation of data? Now, there are ways that it is. They exist in coding systems. This is a way to encode data to represent programs in a way that the computer can understand. There are digital computers, and digital computers is, you can see the diagram over here at the bottom, where digital computers represent things in something we call a state, either something that is on or off. And here are two states. On is a state, off is a state. And this is represented in hardware by the physical opening and closing of a circuit. So if the circuit is closed, it's on, and if it's open, it's off. Or if we look at magnetism, if something has a negative charge, it's off. If it has a positive charge, it's on. So this type of data representation is probably something new and foreign to you right now. You may have some experience with logic or whatnot, but it's likely that you've heard of binary and you've heard these words before, but never really had a chance to dive into them. So when we're talking about representing data digitally, for the purposes of this class, we're looking at turning words, images, things that we can see and tangibly describe with our language into a digital representation, which is kind of on or off or binary. So let's dig a little deeper into that. So here's a diagram here, and it tells us how we can kind of break this out. And the first thing we need to understand is a bit. Now, a bit is the smallest unit of data. Now, here in this diagram, you can see that we have these zeros and ones at the top. Each individual digit is a bit. Okay? And think of it this way. If you had a cookie and you were to bump into it, accidentally drop it, a bit would fall off. Just a little amount. Something by itself that doesn't make up anything significant, nothing you worry about. But let's say that you drop it 8 times. Well, now enough of that cookie has fallen off that we call it a bite. It would resemble that somebody took a bite out of that cookie. That's 8 bits. And a byte is about the smallest unit we can use to express documents or files or programs. And a byte equals 8 bits. Now, of course, 8 bits, as you see here, this string of 8 digits here is not going to be enough to represent a picture of a loved one, or to indicate a trending song, or to even be big enough to hold a song that your favorite recording artist was to record. So what we do is we can think about these bits, well, actually these bytes, in orders of magnitudes. So for example, 1,000 bytes has the abbreviation KB. 1 million bytes has MB. And what those abbreviations are they're actually they're abbreviations of larger quantities. So a kilobyte is 1,000 bytes. A megabyte, 1 million bytes. A gigabyte, 1 billion bytes. Now, something interesting here is that these different prefixes don't necessarily line up exactly with the numerical representation of those prefixes outside of computers. 1,000 in everyday numbers is 1000, but a kilobyte is 1024 bytes. So there's a little conversion here, because computers are in bases of 2, where human beings, we speak in base 10. So this makes a little bit of a difference when we go to representing this numerical data. Okay, so in the binary numbering system, the way we represent numbers is different than how we represent numbers as human beings. Well, and especially Americans, we use base 10. So there's 10 symbols, 0 through 9, and the places have meaning the same way that you would expect. But it's different in the binary numbering system. It only has 2 symbols, so that's a base 2. Okay. Now in both systems, the position of the digit determines the power to which the base number is raised. Now, that sentence, saying it out loud, is even confusing to me. So let's look at an example. Okay. Here we have a picture. At the top, we have a base 10 number, a decimal number, something you're very used to, something you've seen your entire, the whole time you've been in any type of organized education. At the bottom, we have a binary number. This is base 2. Okay. So what we want to do is learn, how can we convert between the two of these? How can we get values that are meaningful? Well, if we take the first row there, well, the first group, you can see that 7,216, each one of those digits represents a power of 10. So 10 to the 0 power equals 1, and 6 of those equals 6. Well, then let's take the second digit in. 10 to the 1 power equals 10. One of those equals 10. So now we know those last 2 digits, in their order they're in, equals 16. Well, the next one, 10 squared equals 100. 2 of those is 200. So now we know it's 216. And then finally, 10 to the 3rd power is, or 10 cubed is 1,000. And there's a 7 there. So we know that it's 7,216. Now with the binary, we still want to take this 4-digit number, break it into placeholders, but instead of powers of 10, we're going to use powers of 2. Okay, so 2 to the 0th power equals 1. One of those is 1. Then we have our second placeholder. That's the 2 to the 1st power. So that would be 2, but we have 0 of those. So our number is still 1. The third one, that's 2 squared. So that'd be 4. We have 0 of those. So that's 0 or 0, 1, and 1. Now the last digit, 2 to the third power. Well, 2 to the third power is 8. So now we have a 1 there, which means we have 1, 8. And then we also have 0 plus 0 plus 0 plus 1. So when we add this all up, we've got 9. So that's how this works. Since we can only represent things, the physical hardware can only let us have something on or off. We have to use bases of 2s to create any number we want. Now you can see how this would work. We could have made a 6. If we wanted a 6, we could have had a 0 in the last column, a 1, and a 0, and that would have been 4 plus 2, which would have gave us 6. We also could have had a 7. If we had a 0 in the first, we could have had a 4 by a 1 there, a 2 by a 1 there, and a 1 here, and had 7. So we can represent the same amount of numbers. It's just that we can only have 2 symbols to do this representation instead of 10 symbols like we have in base 10. This is not a easy task to learn this. This is probably very new to you. You don't have to become an expert in binary. That's not the goal of this course, but you do need to understand how these systems work, how they represent data in states. And I think it's pretty cool to know how to translate between the two of these. And also, it never has killed anyone to learn their powers of 2. It's just good old-fashioned translating this stuff from one system to another, and it helps expand how you see these things. Now, if we move forward, we can see that now we can encode things that we're used to in this bit system. All right, so here's the table. It's the ASCII table. That's the American Standard Code for Information Exchange. And this is what most computers started off with, because many of them original computers were created in America. Well, modern computers. And you can see how they represent each of these different numbers with a combination of one of these 8-bit bytes here. Okay. Now, ASCII was improved upon, and it was improved upon to add more room for more characters, because right here you can see that we don't have a whole lot of space. So we had to improve upon it, and we came up with the extended binary coded decimal interchange code. Okay, and that was developed by IBM to assist in mainframes. Well, computers didn't stop there. Computers continued to get more popular, so then it had to be improved again. And there are other languages. It's not just English, but Chinese, Greek, Hebrew, Tibetan, Russian, Amharic. So there's plenty of different languages out there, so we needed a better system. So we improved upon ASCII and ABIDIC, and we came up with Unicode. Now, Unicode, instead of having an 8-bit 1-byte character, it has 32-bit characters. And that meant that we had a lot more room for symbols. And a universal language in computers was beginning to take shape. So we could represent not only modern languages, but also ancient languages. And this replaced ASCII as the primary text coding system. And those emoji characters that you have on your phone, those are not special images, they are images, but they're not like special glyphs that you have to pull off the internet. The emoji are built right into Unicode. So that smiley face is the same as a letter as far as your computer is concerned. Okay. So now we need to find out how to encode other types of data. We've been looking at text, but how do we do other types of data? Well, when it comes to graphics, stilled images or photos, we use something called bitmaps. Now, a bitmap is a lot like thinking of that grid that you used back in your algebra course in high school, or maybe your advanced math. And it is an image made up of dots, a lot like, I believe it may be Van Gogh, I may be incorrect, but it's where little dots, each called a pixel, make up a picture. And there's an axis, a Y, and an X, and where that dot happens to fall on that axis, the more dots you fill in, the more detailed of a picture you can create. Now, if something's monochromatic, it means it only has 2 colors, so it's 1 bit for each color. But you can still represent a picture, but if it has more than 1 color, we can use a different amount of bits. There's 4-bit, 8-bit. When in my youth, 5-6 days ago, we had 16-bit, and that was exciting. That was Super Nintendo or Genesis. Then we had 32-bit colors. So these different bits represent how many colors you can create. The more bits you have, the more colors you have. So if we look here at a different representation of each one of these color bits in a 16-bit image, 16 color image, 4-bit, you see that we can only get up to 16 different colors, and this is how big a pixel is. It's 4 bits. In a 256 color image, that's considered 8-bit. This is how much information you can encode. And then photographic quality, and this is called true color. Now, true color means there's 17 million colors. Now, your eye is pretty good at distinguishing many of these colors. So to make sure we can match the ability of your eye, we have to have 24 bits to represent 1 color. And the way this is typically broken out, the first grouping is 8. The first group of 8 is red. The second group of 8 is green. The third group of 8 is blue. And that's how we create those colors. Okay. So, to move on a little bit further, we also can encode audio. You're familiar with this, MP3s, Spotify, Apple Music, and this is using bits, again, to represent different portions of audible wavelengths. And, and it's compressed, so we can send it over the internet. And this has really revolutionized, or this has really changed the way audio is done in the world. We no longer use analog versions like a record. It took me a while to remember what it was. Like a record where there's a physical needle going over pits and bumps on the record, but now it's digital. And if we can encode pictures and we can encode sound, well, video is nothing more than pictures and sound. So, of course, this lends itself to video data. And, the way that works is that the images make up the frames, so many frames a second. And then the audio makes up the sound. And then it's a lot of data that goes into this stuff. But if you compress it enough and you've got enough bandwidth, you can send this stuff over the internet. And that's exactly what happens when we're watching Amazon Prime, Netflix, or YouTube. So we took a look so far up to this point. We've looked at binary, how data is represented in computers. We've looked at different ways of encoding it, ASCII and Unicode. So at this point, we're going to take a look at getting a little bit further inside of the computer, right? So we're going to look at machine language, which is binary based, and that's what the computer uses, those ones and zeros. Early programs were using this, and it's still in place. But let's jump inside the system unit. So right now, if you're viewing this video, you've got a computer. Your system unit may be your laptop. If you've got a desktop, you may have an all-in-one system like an Apple iMac or an HP Envy, or you may have a tower if you're at a lab that's either on the floor or beside the computer, separate from the monitor, okay? Well, this is what we're referring to as the system unit. It is the main case of the computer, and it houses the hardware used for processing, storage, the power supply, and it even has a processor in there. And that processor uses memory. It has interfaces to connect the processor to different peripheral devices like printers. And with a desktop computer, it's like a rectangular box. It's probably on the floor, okay? Now, a lot of times when you buy furniture in a box or you do engineering, they have an exploded view where they have popped open the top and show you everything that's inside. Let's do that. If we pop open the top to that unit, you can see there's a lot going on there. We've got hard drives, a power supply, memory, which we call RAM. We'll talk about what that is later. A motherboard, expansion slots, expansion cards, flash readers, card readers, drives, USB ports. All these different pieces play a very important role in creating the computer experience that you've grown accustomed to. Okay, so let's start by looking at these guys one by one. The motherboard is the most important piece. It is the medium that connects everything together. It houses the computer chip, which is a very small piece of silicone we call it semiconducting, so it can hold an electrical charge and it integrates all the circuits. We have the circuit board, which is just a thin board containing computer chips. There's a system board on the motherboard, which allows the circuit board to connect to different devices. We have external things like a monitor, keyboard, mice, and printers. And mostly the external stuff is either input or output. The keyboard is output. The monitor is output. The keyboard is input. The mouse is input. The printer is output. We can do wireless devices such as Bluetooth and even Wi-Fi. We have the power supply in there, which is what gets power to the motherboard. Portable computers have a battery, and some are removable, some are not. It really depends on what you have. But if you think about it, there is a lot going on in that little box by your foot, and you may not spend a lot of time thinking about what's in there, but there's quite a bit happening. Okay, so we covered kind of the motherboard and that. Let's take a look at the front of this unit, these different drive bays, and what's going on there. All right, so when we talk about a drive bay, this is where we can get some storage devices or some input and output. It's a rectangular rack for the most part. It's in the front of the unit. Now for this, I'm really focusing in on the desktop machines that have the Magic Box. This stuff does exist on your Apple computer if you have an iMac, but it is actually just behind the screen, so you can't see it. It's where your hard drive is mounted. It's where your CD drive is mounted, the memory, the card reader, the whole kit and caboodle. It connects to the motherboard with a cable. Sometimes we call that cable a ribbon. And it is for, again, storing work or gathering stuff to communicate with the processor. Now the processor is broken out into a couple little pieces. We have the CPU, which is the central processing unit. It has some circuitry and components that are packaged together on the motherboard, and it does the heavy lifting for the computer. Now the CPU we call it a processor, but a lot of times it's referred to as a microprocessor. And if you're thinking why, reflect back on what we talked about in the last chapter, where these machines used to be the size of football fields, or when they became mini computers, they were the size of entire rooms. So the processing unit was bigger than your couch. Now it's the size of a credit card. And although when you think of micro, we think of something very small at the cellular level, this type of machinery is micro compared to where it came from. To continue on with this, the processors come in a couple different varieties. Of course, there's a single core, but you're not going to find that in too many computers nowadays. So then there's a dual core, which is a processor that has two cores, if you will, or two processing components that can both exist on one computer, one CPU. Now, if there's dual core, we're talking orders of two here, so dual core, next would have to be a quad core. And yes, there is. And if you are following along, you know that has 4 cores in it. Now, This is based on the principle that the more processors we have, the more things we can work on at once. Now, this is true multitasking. As human beings, we don't really multitask. We switch between tasks very quickly. We can do what's called task management. But these machines can actually do some multitasking by processing 4 different things at once in the case of a quad core. Now, different machines or computers that serve different purposes typically have different amounts of cores, and then the personal computer core is made by AMD or Intel. Now, for your media tablets, those have processors made by other companies such as ARM or Apple. And to show you a little bit, let's look at a little chart here. First, in the corner, in the left, we can see that this one i7 chip has 4 different cores, and each one of those represents some processing. Then it has a shared level of memory, and we'll talk about that a little more in depth as we go on. Now, that's for a desktop. That's for a larger machine. For the smaller machines, we still have that type of processing, but it's not going to be branded on its own. It's not going to stand out and say, hey, look at me. It's just going to be something that looks like a little chip soldered directly on the board, okay? And to show you how the power is normally distributed, if we start here at the bottom, these are kind of our least powerful machines. We can see we have the mobile devices, and they go from 1 to 4 cores. Then we have notebooks. They go from 1 to 4 cores, but the power in those is dramatically different. Instead of capping out at kind of 1.9, as we see here, we cap out at around 3 gigahertz in a notebook. Then with the desktop, we start at 4 and go to 6 or 8, and we can get up to 4.2 gigahertz. And then with the server, we're starting at 4 again, but we can make it up to 16. So, when we see the magnified effect, if you have 4 cores at 3 gigahertz, you can get up to like 12 gigahertz in this machine in the optimal environment. But if you have 16 cores, each at 3 gigahertz, well, now we're up to 48 gigahertz. So you can see how this stuff really builds quickly. You can build a very powerful machine with using less physical equipment, but using more processing power within the equipment. Still looking at these different processors. So the central processing unit does the heavy lifting, the majority of the processing. But we can also have other processors inside of the system unit. We've got the graphics processing. This is what we use for games. Now, sometimes they're on expansion cards. Other times they're located directly on the motherboard. But this is used to really take some of the load off of that central processing unit and focus all the graphic stuff, all the stuff that involves images and animations, send it somewhere else to be processed to help speed up the entire overall unit. Now, let's take a look at one example the book talks about is the ride at Universal Studios, Transformers. Well, this one has some very substantial features. There's a 200-foot long track with 14 screens, 34 projectors. The motion of the ride is synchronized with the screen. All the images are in 3D and super high resolution, 4K. And it uses a lot of GPUs to make this stuff not only look real, but also perform the way that you expect it to perform. And this is the power of these different GPUs and processors. They're all integrated in different ways, but they're performing many calculations at a single time. And that is due to processing speed. Okay. So we talked about hertz. We mentioned megahertz and gigahertz. Well, what is that? Well, there is a clock inside of the computer, and this clock synchronizes moving data, transferring it from one place to another, doing those processes. And the way we rate the speed of that clock is in hertz. So a megahertz means that clock is moving, it's got it amped to trigger the CPU at 1 million times a second. The gigahertz is set to trigger the CPU 1 billion times a second. Now, of course, the more times the CPU is triggered, the faster it goes. So the higher the clock speed, the more instructions per second it does. Now, that's measuring how often it processes one individual instruction. But we could also look at it, instead of measuring the clock speed, we can measure the actual speed of how many instructions it can process. And we can do that in what's called a flop. Now think of a flop as one flip of the switch, flipping it from on to off in that binary example we looked at earlier. So megaflops would be 1 million flips of the switch, gigaflops, billions, teraflops, trillions. And these numbers are hard to imagine. Imagine a physical light switch going up and down 1 million times in a second. The speed alone would probably tear it out of the wall. But that's the marvel of this technology, is that inside of your smartphone, there is a little chip that is doing millions of switches every second. And the way that we evaluate this is by doing some benchmark tests. And a benchmark test is where you just perform the exact same test on the machine over and over and over to find out if you are marking the scores on a bench, to make sure the marks always fall in the same place. So to move on, the system unit also is broken out not just in speed, but in how much data it uses at once. And that's the word size. Now, machines nowadays typically are 32 or 64 bit. That's how many bits that it considers one chunk of data, because this processing unit, it works using standardized chunks of data. And something that you can just see plainly in front of you as they think about it, if it can only process 32 ones and zeros, and a machine next to it can process 64 ones and zeros, well, the one that can do 64 is going to be a whole lot faster than the one that can do 32, because it can handle far more data at once. And not only is it handling more data, but the place that it stores this data, the memory, its short-term memory, we call it the cache memory. Well, it's going to be bigger, and the bigger the cache, and the cache is located very close to the chip, the faster it can go. Now, we rate cache memory, or cache, depends on how you want to pronounce it, on 3 levels, 1 through 3. Level 1 is the fastest, and then level 2, and then level 3, each getting a little bit slower. And the way you can figure this out, when you're buying a computer and they say these numbers to you about cache, typically the more, the better. And this isn't something you can upgrade later. The cache is built into the chip itself. So if you can afford to get more initially, it will pay off later. Okay. Just to move on, there's a couple more things in this system unit I want to look at before we break for the second video. There's the bus speed and the bus bandwidth, and the bus communicates from one component to another. This is where data can travel. It's inside of the CPU on the motherboard. And the width is the number of wires used for the data to travel over. Okay. And think of this like a highway on the road. The wider the bus, the more lanes, the better. We can see here illustrated with this that each lane would be a 1 and 0 lane. So that's kind of an 8-lane highway is going to be half the speed, probably a whole lot less than that, than a 16-lane highway. So the more bits you have in your bus, the faster your computer is going to be. And this is the amount that's transferred by it. Now, we've been at this for about 35 minutes. We're going to stop the video here. We're going to pick up with memory and continue on in the next video. So hopefully I should see you just in a couple moments there.